In our quest for identifying the best possible rearrangement of the loop such that there is no synchronization, we first identified the space partitioning constraints. Then we solved the space partitioning constraints to obtain maximum rank functions, fine functions from iteration space to processor space. And then in our last module, we discussed a code generation strategy. Given a set of affine functions, one for each statement, we found a code generation strategy that basically makes the outer loops the processor loops. In other words, the outer loops can be fully parallelized. The outer loops are embarrassingly parallel. And the inner loops are basically loops that are executing one on each processor, and they need to be sequential. And we also said that if it's a parallel machine, that gives you more parallelism. If it's uniprocessor machine, then it gives you better locality because things that had data dependencies are now going to be accessed close in time. In other words, you have reduced the reuse distance. But one of the problems with the code generation strategy that we discussed in our previous module is that the code was not efficient. In fact, the code that is executed for every processor was almost as expensive as the total amount of work that was being done. So in fact, we have increased the total amount of work that is being done. And if it was a sequential machine, it will actually, the generated code would actually be slower than the original program. And so that doesn't look like a very good idea. What was basically the problem is something that we're going to discuss in our module today, and also the solution, which I call tightening the loop bounds. So the solution for the running example that we had discussed in our previous module was that the outer loop basically iterates over the processor IDs. So for example, for P equals minus 101 to 100 plus 100, P plus plus, for I equals 0 to 100, for J equals 0 to 100. If P equals I minus J minus 1, then do something. If P equals I minus J, then do something else. So S1 and S2. And the problem is that I am iterating, for example, in the inner loop over J from 0 to 100, but these statements will only execute for one value of J. For example, S1 will execute for the value of J which matches P equals I minus J minus 1. In other words, it will execute for J equals I minus P minus 1. Similarly, this particular statement, the second statement S2, would execute for J equals I minus P. And so if J, this is, each of these statements is only going to execute for one value of J for a given P and I, then why would you iterate over 100 values of J unnecessarily, right? And those, if I look at any one statement, then out of the 100 iterations of the inner loop, only one iteration is actually doing anything for any one statement. If I look at both the statements, then out of the whole 100 iterations of the inner loop, only 2 iterations, at most 2 iterations, are actually having any effect on the program state at all. Others are just iterating unnecessary. Other 98 iterations are just empty iterations, all right? So that's what I'm calling empty iterations here. And tightening the loop bounds can also be thought of as elimination of empty iterations. And once we tighten the loop bounds, we basically reduce the amount of work that the computer has to do without actually changing the result of the program. In this case also, I can move from J equals 0 to 100 to something which is more tighter, and notice that because it's the innermost loop, I can have lower bounds and upper bounds which are in terms of I and T, because at this point the values of I and T are already fixed. Okay, so to understand this, better, I'm going to use a simpler example than the running example that I have shown you in the previous slide. So let's say my program was simply for I equals 0 to 100, xi equals 0. Now this loop is an embarrassingly parallel loop, but that's not how our algorithm works. I mean, we could have just said, okay, just just put a parallel keyword at the top and we are done. But that's not how our space partitioning algorithm works. What will the space partitioning algorithm do for this example? It will say, okay, what is the iteration space? It's I from 0 to 100. So what is the mapping function that basically obeys the data dependencies? Notice that there are no data dependencies across different iterations. It's an embarrassingly parallel loop. So I'm going to get a full rank solution for my space partitioning constraints. The rank here is only 1. The loop nest depth is only 1. So the solution is just capital C, the coefficient matrix is 1, and small c, the additive vector, is 0. In other words, the processor ID equals the iteration ID. Alright, so P equals I. And it's a one-dimensional processor space as well. So it's an identity mapping from each iteration to each processor ID. And now if I look at my code generation strategy, what is it going to do to this program? It's going to transform it to something like this. It's going to say outer loop is on P, inner loop is on I. So I'm just pasting the original program in the body of the outer loop. And so for P equals 0 to 100, P++, and now I go to for I equals 0 to 100, I++, if P equals I, Xi equals 0. Now, this may look weird bizarre because I've just changed a linear loop into a quadratic loop. Why is this useful? Well, yeah, I mean, in this particular example, it seems like this is wasteful. And in fact, this is the solution that we want to fix right now. And after we fix it, this solution will work not only on this example, but also on other examples which may not have been data parallel, embarrassingly parallel. So in this case, for example, the inner loop has I equals 0 to 100, but 99 of these iterations from 0 to 100 are going to be empty iterations. Only one iteration where I equals P is going to have some effect. And so how can I tighten the loop bounds of the inner loop? I can say something like, it has a lot of empty iterations, and so what I can do is I can just tighten the loop bounds to lower bound is P and upper bound is P. Alright, so from 0 to 100, I've gone to P, which means I've reduced from 100 iterations, of which 99 were empty, to one iteration, which is the non-empty iteration. And so this is what my new code looks like. Now, even this is not very satisfactory, although the number of iterations I are doing is now correct. We're still doing 100 iterations, and the inner loop is only doing one iteration for every outer loop. So the inner loop can actually be eliminated here, and we're going to discuss such transformations later on. But at least we should, in this module, be able to figure out how to tighten these bounds, how to determine these lower bounds and upper bounds. These tighten the lower bounds and upper bounds. And here is a hint. It's not going to be anything that we don't already know. We are basically going to be using the Fourier-Motzkin method to identify the lower and upper bounds by doing appropriate projection of the polyhedron for every statement. Okay. So in this case also, I just basically figure out what are all the for a given value of P, what are all the possible values that I can take for the iteration space of this particular statement xi equals 0, and I basically figure out that the lower bound must be P and the upper bound must be P as well, and so that's how I obtain this solution. So I'm going to discuss this elimination of empty iterations or tightening of loop bounds algorithm in this module. So just to understand what solution we expect for our running example, the example that I showed on the first slide. So we have for P equals minus 101 to 100, for I equals 0 to 100, for J equals 0 to 100, and then something, right? Now, I said that of these 100 inner loop iterations, maybe 98 are empty iterations. So how do I fix that? Well, here is, I'm just going to show you the solution first, and then we are going to see the algorithm to arrive at the solution. So the solution is going to be J equals maximum of 0, I minus P minus 1, and that's J is greater than equal to this, and J is less than equal to minimum of 100, I minus P. And where is this I minus P minus 1 and I minus P coming? Well, notice that it has very striking similarity to these processor mapping functions that I have, which is, I just basically said, because J is now the inner loop, I just rewrite J in terms of P for both the statements, and then basically expand my polyhedral space such that polyhedron such that it accommodates the polyhedrons of both S1 and S2. Okay, so this is the solution. We're going to look at the algorithm very soon. Actually, it is not just enough to tighten the inner loop bounds. We can also tighten the loop bounds of I, because some of the iterations of the ith loop are also empty, because for a given value of P, I cannot usually iterate for all the 100 elements values of I. It does, because these statements are only going to be executed for some combinations of P, I, all right, for all values of J, or possible values of J. And so even here we have some empty iterations, and we can use again the same Fourier-Motzkin method to identify what is the lower bound of I and what is the upper bound of I when I project on I at this point for a given value of P. All right. So this is what the solution is going to look like at the loop at the second loop here, which is I is greater than equal to max of 0 comma p, and I is less than equal to min of 100 comma 101 plus p. So these are the tightened loop bounds. Notice that these loop bounds are strictly tighter, or at least as tight as the original loop bounds, because we are using max and min, and that automatically tells you that we're not increasing the space of iterations, we are only decreasing the space, if anything. Okay, so how do I arrive at these solutions? As I said, we're going to use the Fourier-Motzkin method, and let's just do it. Let's just use the Fourier-Motzkin method on this particular example to see how it will work, and also to review and refresh how the Fourier-Motzkin method works. So we're first going to identify the constraints for S1. Then we are going to identify the constraints for S2, and then we are going to take a union over them. And that's basically this strategy we're going to employ. And so when I look for S1, this is the iteration space. I say, P is between 101 and 100. That's coming from the outer loop. I is between 0 and 100. J is between 0 and 100. P equals I minus J minus 1. And so the way to write P equals I minus J minus 1, notice that for S1, only those iterations will be executed when P equals I minus J minus 1. That was our mapping function, that's the predicate in our generated code. And so I need to basically say, I want to tighten the bounds using this predicate. And so I represent this predicate P equals I minus J minus 1 as a pair of two inequalities. One is P is greater than equal to I minus J minus 1, and the other is P is less than equal to I minus J minus 1. So I just use two inequalities to represent one equality. Together, this inequality and this inequality imply that P equals I minus J minus 1. And now I have all the constraints on my iteration indices in the form of inequalities, and now I can use the Fourier-Motzkin method to project on any dimension. For example, I can first project on P to identify what are the lower and upper bounds of P, and if I just do that, I claim that what I'm going to get is that P lies between minus 101 and 100. This is actually something that we had also done in our previous module when we were trying to understand what is the minimum processor ID and the maximum processor ID that we need to iterate against. But then after we have fixed a value of P, now we can project the remaining dimensions of the polyhedron, which is I comma j, on a single dimension I. And from that we will get the lower bound and upper bound of I. And finally we can, for a given value of P and I can project the remaining dimension j to identify its project on the remaining dimension j to identify its lower bound and upper bound. So that's the simple algorithm, and we know how to solve it using the Fourier-Motzkin method. And this is the solution that I'm going to get using that algorithm. This is the Fourier-Motzkin method again. And so P between minus 101 to 100, I is greater than equal to max of 0 comma P plus 1, I is less than equal to min of 100 comma 101 plus P. So this is just projecting on I, projecting the polyhedron formed by I comma j for a specific value of P on I. And so that just gives me this. And finally, j equals I minus P minus 1. So this is the polyhedron that I get for S1. And let's assume for argument's sake that the only statement in my body was S1, then I could have just gotten rid of S2 completely, in which case I would have already had my solution. My outer loop would have been for P, and these are the lower bounds and upper bounds. The inner loop would have been for I, which these are the lower bounds and upper bounds. And for j, there's only a single value, so I don't even need a loop on j. And I could have just said I could have just said j equals I minus P minus 1 and remove this inner loop completely. And then I could have just executed S1 without needing to have any predicate as well. But the problem here is slightly more interesting because it's slightly more complex, because it has two different statements, S1 and S2. And the polyhedron space for S1 may be different from the polyhedron space of S2. And so let's see what is the polyhedron space for S2. And once again, I just write all the bounds on all the iteration indices. So once again, P is between minus 101 and 100, I is between 0 and 100, J is between 0 and 100, and P equals I minus J. So this time the difference is, in S1 it was P equals I minus J minus 1, for S2 it is P equals I minus J. And once again, when I use the Fourier-Motzkin method to solve to project first on P, then on I, and finally on J, I basically get these lower bounds and upper bounds. Once again, P is from minus 101 to 100. This is the same solution that we had in our last module as well. Then I is greater than or equal to max of 0 comma P. Notice that this lower bound of I is different from the lower bound of I that I had from S1, where it was max of 0 comma P plus 1. Here it is max of 0 comma P. The upper bound of I is min of 100 comma 100 plus P. Once again, the upper bound of I for S2 is different from the upper bound of I for S1. For S1, the upper bound was min of 100 comma 101 plus P, and here it is min of 100 and comma 100 plus P. So 101 and 100. So that's the difference between the upper bound of I. And finally, the lower bound and upper bound of J are both I minus P. And that is also different. In case of S2, it is I minus P. In the case of S1, it was I minus P minus 1. Now, these are the two polyhedron spaces that we have got for each of S1 and S2. And if I take the union, the strict union of these S1 and S2, what I end up with is no non-polyhedral space, because it's a non-convex space, because the union of two polyhedrons need not be a polyhedron. But because we are interested in these kind of affine loop nests, we basically find the tightest polyhedron that encloses this union of two polyhedrons. So the tightest convex polyhedron that encloses this non-convex union of two constituent polyhedra. Okay, and so how do I find that? Well, on the first dimension P, they are identical, so I don't have to do anything. On the second dimension, I just basically take the most liberal answer. So which is more liberal, max 0 comma P or max 0 comma P plus 1? Max 0 comma P is the one that accommodates more values, right? Because P is smaller than P plus 1. And so max 0 comma P now becomes our lower bound for I. And similarly, which is more liberal on the upper bound, min 100 comma 100 plus P or min 100 comma 101 plus P? It's min of 100 comma 101 plus P, which is more liberal. It accommodates more values. And so so basically we get, this is the lower bound for I and this is the upper bound for I. Similarly, when I look at J, I say I minus P and I minus P minus 1, which is smaller. Clearly, I minus P minus 1 is smaller than I minus P. So this becomes my lower bound and for J, and this becomes my upper bound for J. Notice that I can just choose my lower bounds and upper bounds and not worry about correctness, because anyway, all my executions are going to be predicated. So even if I, for example, take a loose upper bound or take a loose lower bound, it doesn't change the correctness of my program. It only changes the performance of my program. So finally, the union looks something like this. P is between minus 101 to 100. I is between max of 0 comma P and min of 100 comma 101 plus P. So the lower bound is coming from S2 and the upper bound is coming from S1. And similarly, J is between I minus P minus 1 and I minus P. Once again, the lower bound is coming from S1 and the upper bound is coming from S2. And now I can rewrite my code to obtain the final generated code. The final generated code basically just changes the lower bound and the upper bound for the two loops in this loop nest. I is from max of 0 comma P to min of 100 comma 101 plus P, and J goes from 0 comma I minus P minus 1 to J min of 100 comma I minus P. So this is our new generated code. I claim that this code is faster than the code that we had generated in our previous lecture module, where we were iterating the inner loop for all the 100 iterations of J, and many of those were empty iterations. This time I'm sure that none of the iterations are going to be empty. Either they will be executing each iteration for P comma I comma J will either execute S1 or S2 or both. Okay, said differently, the number of actual iterations that we are going to execute is going to be the number of values that P can take multiplied by the number of values that I takes for those, each value of P averaged over P multiplied by all the values that J takes over each value of P comma I. And notice that the number of values that J takes is very small. It's at most 2 for a given value of P comma I. And so, the overall number of iterations hasn't become cubic or anything like this, anything like that. Although the code still looks like a triple loop nest, the number of iterations actually remains quadratic. And so that's our desired solution.